So in this example, we have a random sample of size n, x1, x2, all the way through to xn, and we have a particular distribution here, somewhat arbitrary, but it takes on this form. We also know that your x's are greater than 1, so definitely positive, and our theta parameter is also positive. And so using all of this information, what we want to do is find the maximum likelihood estimator of theta, given as theta hat MLE. So as per usual, when computing the maximum likelihood estimator, we just have to find the likelihood function, and that is just the product of all of your individual densities. So that's going to be theta e to the negative x sub I, because we're doing it for each of our x sub i's, minus 1 multiplied by theta. We can then calculate log likelihood, which is just simply the log of the likelihood. And so that really is just the log of the likelihood, which is this quantity here. Okay. So that will go in there. If we take the log of this product, taking the log of a product will result in a summation of logs. And what we can do here is take the log of the first guy, which is ln of theta. And because this is, multiplication, we can, plus ln e to the negative x sub I minus 1 multiplied by theta. And if we just push on here, we get no subscript in this term here. So we get ln theta plus ln theta plus ln theta, a total of n times. So that's going to be n ln of theta. Now, this one over here is going to be plus the sum from I equals 1 to n. And using log laws, the power can come out the front. So we can say negative theta times x sub I minus 1. Okay. And if we take the things that don't have a subscript outside of the summation, what we get is n ln of theta minus theta times the sum from I equals 1 to n of x sub I minus 1. Cool. And really, this is nothing but n ln of theta minus theta multiplied by the sum of x sub I. You can convince yourself that that's just n x bar, because if you think of a mean, the way we take a mean is to sum all the data points and then divide by the number of data points. And then multiplying both sides by n, you just get this quantity here. So what I'm going to do is the sum of all of your x sub i's are n x bar, and then you have minus 1, minus 1, minus 1, n times, so minus n. Cool. And so this becomes your log likelihood. We can then take the derivative of this with respect to theta. So del L on del theta is going to be, taking this derivative with respect to theta is just n on theta. Taking this derivative with respect to theta, we can just extract everything that's not theta, essentially. So we're going to get minus nx bar minus n. And to find the maximum, we can set it equal to 0. And that will just be for stationary points. We're going to have to prove that it is, in fact, a maximizer. So solving for theta, we can times everything by theta. So n minus theta times nx bar minus n is equal to 0. We can take this entire term to the other side. And so that becomes theta times nx bar minus n is equal to n. And so dividing by everything that's not theta, we get theta hat, according to maximum likelihood estimation, is just n over nx bar minus n. We can divide by n, so that's going to become factorize an n out, and we get that factorization there, in which the n's cancel, and you're left with 1 over x bar minus 1. Cool. And ultimately, all that we have to do now is just show that this is a maximizer. So taking a look at our first derivative, we got del L on del theta is equal to, that really is just n theta to the minus 1 if you write as a nice looking power. And then this guy here has no theta, so I might just say plus some sort of constant. We're not too fussed about that because there's no theta in this term. And if we take the second derivative, del squared L on del theta squared, that's just using power rule, negative n theta to the minus 2, which is going to become negative n over theta squared. And this guy is negative because theta squared, well, I mean, theta's positive, so theta squared's definitely positive, and n's just the size of our random sample. So we have a negative quantity over a positive quantity, which of course is negative. And that shows that this is ultimately a maximizer of our log likelihood.